Okay, excellent. So we're happy to have Saeed speaking to us today. This is Saeed's second year at TTIC as a research faculty, and Saeed works on interesting problems in the intersection of learning and algorithms with incentives and strategic behavior. And we'll hear Saeed talking to us about Bayesian strategic classification today. Thank you.
Thank you, Nancy. All right, yeah, so today I'm going to tell you about Bayesian strategic classification, and this is based on joint work with Lee Cohen. She was at TTIC last year, now she is a postdoc at Stanford. Kevin, where are you? He was here like 5 minutes ago.
Should be here.
Kevin should be here, he's a PhD student here. Ali, who's sitting over there, is a research faculty here at TTIC, and Juba Ziani, who is an assistant professor at Georgia Tech. Right, so before we get to Bayesian strategic classification, let me tell you what the strategic classification is without it being Bayesian. So imagine we are in an algorithmic decision-making framework where there is a learner, a company, a firm who's using a classifier to make decisions for individuals, and we might sometimes call these individuals agents. For example, in loan applications, you can think of a bank using an algorithm, a classifier, to decide whether someone should be given a loan or not. And the concern in strategic classification is that in some applications, like hiring or loan applications, individuals might have some knowledge of the classifier that the learner is using for classification. And in these settings, individuals do benefit from positive classification. So what happens is that given their knowledge, individuals might strategize at a cost to look more qualified than they actually are. For example, in loan applications, people know that higher credit score is better, is going to increase your chances of getting approved for a loan. So a person might open new credit card accounts to lower their credit utilization and increase their credit score artificially. And obviously, this is not going to increase the financial abilities of a person. It's just a hacky way of gaming the system and increasing their credit score. Or in hiring, you can imagine that candidates might memorize some answers, to common interview questions. And again, this is not going to make them a more qualified candidate. It's not going to make them more knowledgeable. This is just a hacky way of gaming the system. So these are the concerns in strategic classification. Agents, given their knowledge of the classifier that the learner is using, might strategize. And the goal of the learner here is to design a classifier that is accurate in the presence of such strategic manipulations. All right, let's formalize this a little bit. So agents are represented by pairs of x and y, where x is a feature vector, and y is a binary label of the agent. Think of 0 as being not qualified and 1 as qualified. And let's imagine that there exists a function f that governs the relationship between x and y. For each x and y equals f of x. And there is a distribution D over the space of agents. And the cost that the agents pay to do this strategic manipulation is captured with a cost function C. So if an agent that is located at location X in the space of individuals moves to a new point C, their cost of manipulation is going to be C of X and Z. And this is just a real valued number. And one important assumption here is that manipulation doesn't change one's true label. If someone is unqualified and they manipulate to a point such that f of that point is 1, their label remains 0. They're not qualified. And we take a class of functions, a class of classifiers. Each classifier is a mapping of feature space to labels. As the hypothesis class that the learner is using, the learner wants to pick a classifier from this class to classify individuals. And given this formal model, a strategic classification is defined as a game between the learner and the agents. So in this game, the learner goes first, it releases a classifier H and this class of functions that it has. And then after agents observe this classifier, every agent best responds to this classifier by manipulating to a point that maximizes their utility. And what is the utility of the agent? The utility of every agent is simply their classification outcome minus their manipulation cost. So every agent X tries to find a Z that maximizes H of Z minus the cost of manipulating from X to Z. And we call, let's call an optimizer, a maximizer of this function by best response of X and H, ER, X and H. And given this, the goal of the learner is now to release a classifier in H that maximizes its strategic accuracy. And what is the strategic accuracy of a classifier for a given classifier H? The strategic accuracy is simply the probability that H agrees with the ground truth function F after agents do this manipulation, after agents best respond to the classifier H, which is captured by this best response of X and H. Right? So this is the problem that the learner wants to solve in strategic classification. And I'm going to show you a simple example showing that this problem can be solved in certain applications. So imagine that the space of individuals is the d-dimensional Euclidean space, and the function that labels individuals is just a simple linear threshold classifier. And the cost functions that the agents have is simply the L2 norm of the difference of the points. So if an agent goes from X to Z, their cost is going to be the L2 norm of Z minus X. So this is the ground truth function. Anyone above F is positive, anyone below F is negative. And if the learner just uses F for classification, what happens is that there will be some negatives which are close to the decision boundary of F, which will manipulate to the positive side of F and get classified as positive. So if the learner uses F, then there's going to be some error, some strategic error. But now the question is, can the learner do better? Is there a way to get, say, perfect accuracy? And the answer to that is yes, if the learner instead shift this classifier F by 1 and get this new classifier H, then if, I want to argue that if the learner uses this new classifier H, then it's going to achieve perfect strategic accuracy. Because what happens is that when H is used for classification, the negatives that are all the people below F do not have any incentive to manipulate because their distance to the positive side of H is more than 1. So they would have to pay a cost of more than 1 to get there. But the payoff that they get is just 1. So they're not incentivized to manipulate. And the positives that are in this strip between F and H, because their distance is less than 1 to the positive side of H, they do manipulate and go to this positive side of H. And the positives that are above H, they just stay there because they're already classified as positive by H. So what happens is that negatives stay below F and all the positives will go to the positive side of H. And so if the learner uses H, then the learner achieves perfect strategic accuracy. Everyone will be perfectly classified correctly. All right, so we saw strategic classification, an example where we see how we can make a classifier robust to strategic manipulation. But the thing that I want to mention here is that, or like emphasize, is that the common assumption in strategic classification is that agents fully know the classifier that the learner is using. Like, they exactly know all the parameters that the learner is using, but obviously this is an unrealistic assumption because in practice people have some knowledge of the classifier. They don't exactly know what that classifier is. like in loan applications, people know that higher credit score is better, but they don't know what the corresponding parameter for credit score is in the classifier that the learner is using. And because of this limitation, this is a strong assumption, we propose a model for strategic classification that instead model agents as having a distributional prior, pi, over the class H. And this distribution captures the belief of the individuals about the deployed classifier of the learner. So for every little h prime in this class H, pi of h prime is going to be the probability that the learner is going to deploy h prime for classification from the agent's perspective. And one thing I want to emphasize here is that the learner in the model that we propose is committed to use a fixed classifier h, which is fixed before any interaction occurs between the learner and the agents. So with probability 1, the learner is going to use some h. And this distribution pi basically captures the belief that the agents have about the deployed classifier of the learner. And the only assumption that we make about pi is that the support of this distribution must contain the deployed classifier of the learner, which is h. So this.
Do you make any assumption there on the minimum probability in the support?
Yeah. The probability can be anything, can be arbitrary. So all we assume is that the support includes the deployed classifier.
So if I understand correctly, pi doesn't actually depend on h. Like I don't, like people's belief about what I'm going to use is not actually informed by what I'm actually using.
Correct. In theory, there is not like a formal relationship between the two. But the story that we have in mind is that when telling this, model is that the learner has been using H in the past. Like this is like a fixed, classifier that the learner has used in the past to for hiring.
H.
And and agents over time have acquired some information about this H that the learner has used, and this is how the pi is formed.
So that pi does depend on h.
And in the motivating story it doesn't.
But here, you're gonna fix pi and then ask us how to choose h. No.
But from the support of pi. It should be in the support.
Okay, maybe we'll. I mean,
Yeah.
what's the game here? You fix pi. I mean, as the principle.
And the
What
point
do
here
I-
is that the H is fixed. This classifier that the learner is using, that's fixed.
Yeah, I'm
That's
the
the-
learner. I'm the
Yeah,
learner.
you have a fixed H.
But how do I choose h after knowing pi?
No, you have a fixed H, and the goal is going to be releasing information. Like the optimization of the learner is going to be how to release information about this
So I
digital
have
classification.
h and I'm gonna release pi.
Yeah.
I have h.
No,
and
the pi is for the agents. Agents come up.
You haven't gotten to the game yet.
Oh, okay. Okay.
Maybe it will be clear.
Just
Alright.
a quick question. So shouldn't we expect that somehow that minimum probability appears in the bounds? Because if you have a points mass, that means common classifier is known by the agents, then you expect to get the previous result.
So, the assumption that we have,
Like the prior being very off.
yeah,
The accurate prior that is a points mass on the actual classifier being used, it should make a difference, right? Somehow.
yeah, that does play a role, yeah. Alright, so given that the agents do have partial knowledge about the classifier, we also equip the learner with the ability to release partial information about the deployed classifier H. And the goal here is that using partial information release, the learner can influence the belief that the agents have in order to hopefully gain in accuracy. Another question is, how do we model partial information release? We consider a general model for information release, which is taking a subset of the classifiers in the domain and then releasing them. And releasing a subset of the classifiers simply means for the agents that the deployed classifier belongs to the subset. That's how the learner releases information. So this gives the learner a spectrum of information release. On one end, if the learner chooses this subset H to be the entire class. And that's basically giving no information to the agents, and that's what we call no information release. And on the other end, if the learner chooses H to be just the classifier that it's going to deploy, then this is giving full information to the agents, and we call this full information release.
Quick question. So should I think of this as a special case of Bayesian persuasion where the classifier is a state of the world, you commit to information design, there is a prior
But there is a restriction here, I'm gonna tell you the next slide, that we restrict only to truthful information release. The learner,
right, that's a persuasive construct, I assume, on the information, the signal that you send to the agent.
And I just want to quickly mention that this is like a general model of information release. For example, common ways of releasing information that you can think of: releasing the top K features of a classifier, or releasing the relevant features of the classifier, the features that have non-zero weights. These all can be captured in the subsets of the model class. Alright, so we have this information release model, and the only thing that we restrict ourselves to is that we ask for truthful information release, meaning that subset H must contain the deployed classifier. The learner cannot lie to the agents and give them wrong information because they assume that's going to be illegal or problematic.
So I can think of this as you're releasing promises. They have to be true promises. But I can say, this thing does not matter, or this just some properties, and they have to be true. And it's just deterministic properties that then allow the others to restrict the set.
Yeah, exactly. And what happens after the learner releases a information H? What happens is that the agents first update their prior belief pi by projecting this distribution onto subset H, and we denote this new distribution by pi sub H. So how does this projection work? For every H prime, the probability weight under pi sub H is going to be the probability weight under pi normalized by the probability mass of subset H, if H prime is a member of H. If H prime does not belong to H, then this probability is going to be 0. So this is how the agents update their prior and get their posterior belief. And then after, the agents best respond by manipulating to a point that maximizes their utility. And what is their utility? In this probabilistic setting, the utility is the probability that the agents receive a positive classification outcome minus their manipulation cost, where the probability is now computed with respect to the posterior belief pi sub H. So the utility of manipulating from X to Z, given that the information observed is H, is going to be probability that H prime of Z is 1 when H prime is sampled according to pi sub H minus C of X and Z, the cost of manipulation. All right, with this model, we now have the strategic game with partial information release.
Can I ask a question? So they just need to best respond to the H prime that has highest probability according to their belief.
What do you mean by that? This is
So they have a probability distribution over these family of classifiers, and they just take the one that has highest probability, they classify them as 1, and they just need to best respond to
That's
that.
not what you.
Yeah, but it's complicated by the. Oh, sorry.
Wait, that's not what you define. Right?
yeah, but there's also this cost function.
But cost isn't it the same for all
So
classifiers?
maybe passing a classifier which has the highest probability is too far from you, so the cost of manipulation.
Cost is different,
Or,
depending
or,
on
or maybe
but-
or maybe one point gets a bunch of classifiers across.
But also, so you're integrating over this pi, not taking the most likely one.
Yeah, this is
The agent is
Yeah.
maximizing the expected
Yeah,
utility.
the expected.
it's
So it's not-
expected, yeah, it's
right, so
expected.
it's
But it's not the
most-
cost, but
it's not-
it's the probability of it. So it's the Z. So move to the point Z that has the highest likelihood. Not pick the H first and then go. not make the H prime first.
Just do the Bayesian
why do you call
update,
this
now you
likelihood
have a
adjustment?
distribution, you maximize your expected utility given that it's distribution.
It's a probability, yeah, maybe probability is
Just-
better. But the point here is that there is a z here and there's also a z here. You cannot just optimize this. Find the one that maximizes your probability.
Actually, I feel like this is probably where we're most different from Bayesian persuasion. Like the cost function will complicate, like a non-Bayesian persuasion. That's great.
Okay, so we denote this manipulated point of agent x by best response of x to the subset h. And then the goal of the learner is to release a subset of the classifiers. This is the partial information that the learner releases, such that first this subset includes the deployed classifier h, and that it maximizes the strategic accuracy for the learner, which is again the probability that h, the deployed classifier, agrees with f after agents do this manipulation or best respond to the information released.
So I think I understand just to make sure. So the game here is H is fixed. I don't get
No, H is
as the learner. I don't actually get. There's no learning. Like I don't get to change H.
Yeah,
Or there's no decision making even. I can't get to change my predictor. I only get to release information about it.
Yeah, so maybe like choosing the word learner is not like the best here, maybe like a firm, like a company.
Right.
Because
But the point is I don't have any control over that. So some other
Yeah.
department already
Yeah.
decided
Yeah,
what
learning-
predictor to use, and I only get.
Yeah.
I'm just the PR person.
yeah, you just want to use a fixed classifier, maybe it's
Yeah.
costly to change it, and you want to optimize for information release, yeah.
So like one way to say this could be like we're choosing how like bright of a flashlight to shine on our own classifier, like yeah.
That's it. Alright, so before I move on to tell you about our results, you might ask that, is this model even helpful? Like, can the learner gain in accuracy by releasing partial information instead of full information? Like, we want to have a comparison of like, partial information release versus full information release, which is considered in the standard setting of strategic classification. And the answer is yes, there are examples where if you release partial information, you gain in accuracy compared to full information of standard strategic
And no
classification.
information. So, and no information.
No, look here, I just want to compare it to the standard setting of a strategic classification, which is giving full information. You release your classifier. But yeah, we do have this is not the example for it, but we do have other examples showing that like even it's better than no information. So imagine that your agents lie in this interval from 0 to 2, and your distribution is uniform over this interval. And the ground truth function is going to be a threshold on 1.9. Anyone bigger than 1.9 is a positive, anyone smaller is negative. And because of this structure, we work with threshold functions in one dimension, where the threshold can be any number between 0 and 2. And we denote these by h sub t. And the cost function that we take for the agents is simply the following. The cost of moving from x to z is z minus x if z is greater than x, and it's 0 if it's smaller than x. And this is because increasing your x only increases your likelihood of receiving a positive, being a positive. So like in that direction it's costly, but it's decreasing your x should be for free because you're not going to gain anything. Alright, and for this particular example, we can show that if we use the standard setting of a strategic classification, which uses full information release of the classifier, the optimal accuracy that the learner can achieve is going to be achieved by h2, which is the threshold function of 2, and its corresponding accuracy is going to be 0.55. And why is that? Because once the learner picks h2 and releases that to the agents, all the agents between 1 and 2 do have incentive to manipulate to 2 because their distance to 2 is less than 1, and if they go to 2, they get positive classification. So they're going to get positive utility if they just move to 2. But out of all these agents that are located between 1 and 2, the ones that are located between 1 and 1.9 are negatives. and they manipulate to 2 and they get classified as positive. So this corresponds to the error region of the classifier H2. And so the error rate is going to be the weight on this inner wall, which is 0.9 divided by 2, 0.45, and the accuracy is going to be 1 minus error, which is 0.55.
Can you ask me a question kind of again? So I understand the kind of micro foundations of the model, but at the end of the day, this is a special case of Bayesian persuasion, one-dimensional version. Or is there any part of the model that is not part of it?
I'm not,
The cost doesn't make a difference because that's just a part of the utility of the agent that does not depend on the state. I don't think that makes any
yeah,
difference.
it could be, but one thing that, like, I'm not familiar with Bayesian persuasion, but one thing which I thought was different is that in Bayesian persuasion, you don't ask for truthfulness of the signal, but here we
You do. That's the persuasiveness part. So this, you need to send the there's an incentive constraint in Bayesian persuasion.
I see. Okay.
I mean, this has a structure, so probably you're gonna say something about it, but I still don't see whether this is really not a special case of Bayesian persuasion or yeah. But we can take it up.
Maybe you look clear later, yeah. Okay, so we saw what full information release does for this example, but now let's look at partial information release. Suppose that the agents have this prior, they think that the probability 0.9, the deployed classifier is going to be a threshold at 1.8, and with probability 0.1, the deployed classifier is going to be a threshold at 2. This is what the agents think. And here, if we release this subset, which is exactly the support of this distribution, and it's basically giving no information to the agents, then the posterior distribution for the agents is going to be exactly like the prior. It's not going to change the prior. And now the next question is, how do agents manipulate? What happens is that under this information and under this posterior belief that the agents have, you can show using the utility function of the agents that the negatives in 0 to 0.9 stay where they are. They're not going to manipulate because they're not going to get any positive utility by manipulating to a point. The negatives between 0.9 and 1.8, they're all going to manipulate to 1.8 because they get a payoff of 0.9, which is the probability that they think is going to be the deployed classifier, and their distance to 1.8 is less than 0.9. So, and the negatives in 1.8 to 1.9, again, do not have any incentive to manipulate, and all the positives, which are located from 1.9 to 2, they're all going to go to 2. This is just a simple calculation based on the utility function of the agents. So to summarize this, like all negatives are going to be located somewhere less than 1.9. All the positives are going to be located at 2 after they manipulate. So if we release this partial information, which is this set at the threshold classifier at 1.8 and the 1 and 2, and when H2 is deployed for classification, then we have perfect classification for everyone. Like the learner achieves perfect accuracy for 1, which is bigger than 0.55 of full information release. This example shows that yes, there are cases in which if you release partial information about the classifier that you're using, you can gain a significant amount in the accuracy.
Does the learner know the prior?
Yes, that's a good question, and we assume that the learner does know the prior, yeah.
And is this the only way that you can release information, pick a subset of the classifiers that contain the state of the robot?
Yeah.
I think that makes it a little bit different from Bayesian persuasion because there is no commitment to a signaling scheme.
Yeah.
There you can do more, you can send the richer signal, but there is also a stronger assumption because of the commitment to information itself at the beginning.
Question?
So yeah, I'd like to ask the following. It feels like if the learners know that know the function that if the agents know the function that the learner is trying to optimize. So like in this example, that the learner only wants agents whose value is 1.9. So like in this case, it feels like the classifier of 1.8 is in some sense not credible, as like I'd expect that the learner would want us to at a minimum set their threshold for to be like the minimum that they want to accept.
So you're asking, like the learner wants to choose classifiers that are bigger than 1.9, not anything is smaller than that.
Yes. So as asking, like if you have another example off the top of your head where the learner is only choosing like classifiers which are at or above their actual threshold.
And so here, this 1.8 is like what the agents believe, and they may not know what the function f is. But this is like a example that we constructed and it worked. We showed that partial information is better, but I don't know off the top of my head if there is an example that satisfies the constraint that we have. But that's a good question. Any more?
I was, it's like a follow-up. So I was wondering if the learner can also give out distributional information, like releasing a subset of the classifiers is like saying I'm getting uniformity from them, or it could be a different update.
Right, that's like the Bayesian definition. So coming to conditional distribution on the signals.
Yeah.
Without lots of change, it can be just classified that you recommend.
Yeah, like we work with deterministic information release, but yeah, there is an interesting question of if the learner can release probabilistic information. And yeah, that's a good question.
But what does this mean in this case? If the predictor is fixed.
Yeah, like that's the subtlety. Like
Right. So
if the predictor is fixed, if the classifier is fixed, then releasing probabilistic information, it feels tricky because you have fixed your classifier before. Like you're not going to
commit to a
send.
conditional distribution
Of what?
of, let's say I recommend you a signal, and imagine that the conditional distribution for what I recommend, conditional on what is realized as the fixed classifier.
But your predictor is already determined. They can't you
So
can't.
I think the game is that at time 0 there will be a predictor realized from the prior, and then the game is going to play it after.
No, but now you're changing your predictor. But the whole setting here is the predictor is you have no control over the predictor, if I understand correctly, right? The predictor is fixed. You can't actually change it.
Yeah, it does.
So imagine nature is drawing the predictor at time 0 from the prior, and now the game is played.
To be clear, you guys are describing different games. That's
Right,
what
like
you're
this
doing.
one-
You're
No.
describing this game, you're describing Bayesian persuasion, right?
Right. So in this game, it's different, right? Because the predictor is fixed.
Yeah.
That's typically made a difference. So you don't get to choose the predictor. You don't get to affect the predictor in any way.
There you
So the
are.
prior is not accurate. I mean, there's no sense that H was actually drawn from I.
No, H is fixed. Yeah,
Right.
prior is just the agent's belief.
No, but prior has H in the
Yeah,
support.
it just has H in its support.
But if I can choose any other prior that
Who
has
is
H in
you?
the support, so the learner
Uh-huh.
can choose any other prior that has H in
So
the
the
support.
learner doesn't draw from the prior.
I know.
Nature actually does.
Right. So no, nobody draws from the prior.
So in the game I'm describing, which is the generalization of this, there's a nature that is drawing classifier from the prior at time 0.
I understand.
Right.
But what I'm saying is to me and this is what I'm also kind of confused by this, because the main difference is in the game you're describing, the learner has control over the predictor. The agent that's called here learner has a control over the predictor. Whereas in the setting described here, if I'm understanding correctly, you have absolutely no control over the predictor. You don't choose the predictor, you cannot control it, you cannot affect it. Like nothing you do, your actions are not going to affect the predictor.
You can talk offline, but in the game I'm describing, you also don't have any control over the predictor.
But I thought you said you choose a prior and then the predictor is drawn from the prior.
So there's a prior given that defines the game. Something is drawn from the prior. Now, I as the principal, in this case, the learner, I see that, I recommend the agent a classifier. And then the agent may or may not accept my recommendation. You design the recommendation so that it is.
Okay, so that's maybe a bit.
Right.
Okay,
It
so
is, it's very relative.
Okay.
Yeah.
Let's move on from discussion. So another question is like we have this model, like the important problem here is the learner's information release problem. Remember that the learner is facing a population of agents with prior pi, cost function c, and their goal is to maximize their strategic accuracy. And note that here, including anything outside the prior support in H is not going to influence the agent's best response. Because at the end of the day, agents are going to project their prior onto this subset H. So if you include anything in H that's outside of the support, it's not going to influence it. So we can rewrite this optimization problem as maximizing over all the subsets of the support of the prior. And one naive algorithm here is to enumerate over all subsets of the support of the prior, which is inefficient. And now the question is, can we do better than this very naive algorithm? And to do this, we need to make some extra assumptions, or we need to have some structure in our problem. So we consider classification of agents based on real valued test scores. So there exists a function g, this is the test, and the ground truth function f is simply an indicator, a threshold function on g. So anyone whose test score is larger than t is a positive, and anyone who's smaller than t is a negative. So higher values of g correspond to higher test scores, and therefore they're better for the agents. And given this setup, a natural way of formalizing the manipulation cost is going to be the following. The cost of moving from x to c is going to be g of c minus g of x if g of c is greater than g of x, and it's going to be 0 if g of c is less than g of x. And again, this is because higher values of g are going to be better for the agent. So increasing your g value is going to be costly, but decreasing it should be for free. And given this structure, we work with threshold functions and g. That's the hypothesis class that we work with. And if you're familiar with the work of Hart et al. In 2016, the paper is called Strategic Classification. This setup is exactly the setup that they considered in their paper to provide computationally efficient algorithms for strategic classification. They introduced the notion of separable cost functions, which are exactly the costs that look like this. All right, so to avoid talking about this g function and to make our life easier, have simpler notations, we consider agents that live in the one-dimensional space. Every agent is just a real valued number. Think of this real valued number as the corresponding test score of the agent. There's a threshold t such that f of x is the indicator of x being larger than t. Higher values of x are better. And the cost of manipulation is from x to z is going to be z minus x if z is greater than x, and it's going to be 0 if c is smaller than x. We work with threshold functions and R, and from now on, for simplicity of notation, I will use H as both a mapping, or like a classifier, and a real valued number, which is going to be the corresponding threshold of the classifier. And the same thing for F.
So does the situation you described earlier where the cost was the L2 distance, does it map into this way?
So here I'm assuming that the agents live in the one-dimensional space. Like there is one test score that I'm going to use for classification. That L2 was in a two-dimensional, or at least two-dimensional space. And let's see what the agent's best response problem is going to look like in this setting. Remember that every agent wants to maximize its utility, which is the probability of getting a positive classification minus the cost of manipulation. And under this setup that I just introduced, we can rewrite this as the probability that z is greater than h prime minus z minus x. And this is, again, because of what I just said. I'm gonna use h prime as the corresponding threshold. So h prime of z is 1 if and only if z is greater than the threshold of h prime, which I use h prime for the notation. And again, agents are not incentivized to move backwards to make their x smaller, so that's why this maximization is over all the z's that are greater than x. And we can rewrite this as, this is going to give us a simple optimization problem, which is maximizing the CDF function of pi sub h evaluated at z minus z. Okay, so there is a simple way to compute the agent's best response, and we can further show that for any agent and any prior pi over a set h1 through hn, the best response of the agent to any subset h is going to be either x or any hi's in h that are bigger than x. So it means that every agent either stays in its location or finds an hi in the subset h that is greater than x and manipulates to that point. But the more interesting problem here is the learner's information release problem. And we start with a negative result. We show that for an arbitrary prior pi over a set of threshold classifiers h1 through hn, the optimization problem that the learner wants to solve is NP-hard. Solving this is going to be NP-hard, and this is using a reduction from the subset sum problem, which is known to be NP-hard. What is the subset sum problem? We have a collection of positive numbers, and the goal is to decide whether there exists a subset of these numbers, such that if I evaluate the sum of the data points, sum of these A numbers on that subset, it equals the half of total sum.
I'm assuming D is specified here as an empirical distribution, or when you talk about NP hardness, how is D is an input, right?
D is an input, yeah. For any D, this is a.
Oh, so
for any fixed D, yeah.
That's a bit too strong, right? It's not for any fixed D. D is a point mass.
Yeah, we construct a, yeah.
So you construct the D.
Yeah, you reconstruct the D, yeah.
But you're viewing D as not part of the, D is fixed, it's not an input to the problem.
Yeah. So this problem is NP-hard, but are we doomed? Should we stop, or what do we do here? Again, like similar to all the research in computer science, in order to circumvent hardness results, we make assumptions about the board. So we're going to assume that the prior distribution is uniform. We showed that for arbitrary priors, the problem is NP-hard. So now let's assume that the prior is uniform over a set h1 through hn. I remember that we make the assumption that the support of the prior does include the diploid classifier h. So for some k between 1 and n, hk is going to be h. And one thing we show here is that the accuracy, the corresponding accuracy of any subset h is going to be characterized by a real valued number, which is r sub h. And this r sub h is simply the smallest x value such that the best response of x to h is going to be larger than the threshold for the diploid classifier h. So this is simply the smallest x value or the agent that can manipulate and pass the classifier h.
Quick question. So do you think of n to be a little bit small? Like, because if n is large enough, then I can simulate any prior using uniform distribution. I just like repeat the same.
That's a good question. We did not think of that, but we assume like n could
Maybe
be
it's not a
large.
multiset.
Like, yeah. We allow n to be, or no, like we do
You
assume
really
that.
want the uniform distribution over everything that is in your set.
Yeah. So what we can show here is that the corresponding accuracy of releasing a subset h is going to be characterized by r sub h, and this is the exact expression. Accuracy is going to be 1 minus the probability mass of the probability mass between the minimum of RH and F and the maximum of RH and F. And you can think of this as the probability mass between RH and F, depending on which order is smaller, which order is larger. And then what we show next is that we show that when the prior is uniform, R sub h that characterizes the accuracy of the learner can take only polynomially many values, even though there are exponentially many subsets h. And to do this, we consider the following partitioning of the space of the subsets of the classifiers. So on the left-hand side, we have all the subsets of the classifier. And this is the search space of the learner. And we want to write that, we want to partition that as the union of SLIs. And what is SLI? SLI is simply all the subsets, all the H's, such that first H includes the deployed classifier H. The size of H is L. And the best response of an agent, which is located at H, to this subset is going to be HI, which is an element of the support of the prior. So we consider this formal partitioning of the space, and what we show is that if the prior is uniform, then for any subset H and SLI, R sub H is going to be HI minus J over L for some J between 1 and N. So what this tells us is that we have only N possible values for I, N possible values for J, and N possible values for L. So the number of possible RH values that we have when the prior is uniform is going to be only polynomially many. So the algorithm that we propose is going to look like this. For any possible values of L, I, J, we first compute a candidate value for R, which is HI minus J over L, and then we efficiently construct a subset H such that R sub H equals R, if such H exists. And then at the end, we output the subset H that maximizes the accuracy of the learner, and the accuracy is specified by this expression, which I showed you in the last slide. It's just a function of R sub H. Right, so to summarize this part, there exists an algorithm such that for any N, any uniform prior over H1 through Hn, and any data distribution D, this algorithm returns a subset H star in time NQ, such that H star does include the deployed classifier H, and that H star maximizes the strategic accuracy of the learner. Right, so we have the result for uniform priors, and we work with discrete uniform priors. And we also saw if we can get better results if we assume that the prior is continuous instead of being discrete. So we took pi to be uniform over an interval in R, and the learner's information release here is basically releasing a subset of this interval, a subset C and D, such that the deployed classifier does belong to this subset. And we can show that the optimal information release in this case can be computed easily, and in fact there is a closed form solution for it. So under this setup, when the prior is continuous uniform prior, we can show that the learner can find the optimal values for C and D, and these are the expressions which are not important. And so far we've been working with strategic accuracy as the objective of the learner. So the learner kind of views false positives and false negatives equally, it just wants to minimize the misclassification error rate. But there are settings in which the learner's objective is to minimize the false positive rate or false negative rate. For example, in hiring, a false positive could be bad because if you hire someone and they turn out to be not qualified for the job, it's going to be costly. But a false negative is not that bad. If you miss a good candidate, you know that you're going to see another good candidate. So there are applications in which minimizing false positive rates or false negative rates are preferred, and these are the exact expressions for these false positive rate and false negative rate. And the question that we ask here is that what does the optimal information release of the learner look like without restricting ourselves to uniform priors? And we do have some results here. First, we show that for any prior pi, if your objective is to minimize the false negative rate, then you might as well release the classifier that you're using. So the false negative rate of just a single classifier h, which is the deployed classifier of the learner, is going to be smaller than the false negative rate of any other h that you can take. So full information release is optimal for false negative rate minimization. And then we took false positive rate as the objective. Here we cannot show that what the exact optimal information release looks like, but one thing that we can say is that when your objective is false positive rate minimization, then releasing nothing is going to be better than releasing everything. The false positive rate of the class H, like all the classifiers in your class, is going to be smaller than the false positive rates of releasing only the classifier that you're using. And we complement this theorem and show that for false positive rate minimization, there exist examples in which full information release is optimal. In another example, no information release is optimal for the learner. And there are examples in which neither full information nor no information release is optimal. So you have to pick like a somewhere in between partial information release. All right, so this is all I wanted to tell you about the results we have, and I want to wrap up with some interesting direction for future work. And one direction is fairness. The majority of the works in fairness in strategic classification usually look at population groups that have different cost functions. Like for one group, it's going to be easier to manipulate. For the other group, it's going to be harder. And they look at the effects of having different cost functions on the outcomes that agents get. But another cause for unfairness could be that population groups have differing beliefs about the classifier that the learner is using. And this is exactly captured by this prior distribution that we have in our model. So our model allows the study of fairness in a strategic classification when different groups in the population not only have different cost functions, they also have different prior distributions. And one question that you might ask is that what if one group has like the better prior and also the better cost function? For example, there are two groups, the disadvantaged group, the advantage group. And it is natural to assume that the advantage group not only has a better cost function, their manipulation cost is going to be smaller than the disadvantaged group. They also are better informed. They have a better prior over the class of functions. Another question is, can we release information in a way that helps the disadvantaged group? And all I want to show here is that there exists a motivating example that answers this question, and the answer is yes. Suppose that we have two groups with these priors. The prior for the advantage group gives probability weights of 2/3 to the deployed classifier H, and it gives probability weights of 1/3 to another classifier H1.